let's look at Chapter 3 in the Geometric Dimensioning and Tolerancing book. Chapter 3 is going to be a little bit of a review, but I feel like it's an important review. The work that we're going to be doing in class, Geometric Dimensioning and Tolerancing, really relies on a strong foundation of dimensioning. That is to say, understanding how to dimension, where to apply the dimensions, how to apply the dimensions, and just a good understanding of what dimensioning is intended to achieve. So this is a review that I feel like is very important to lay the foundation or the groundwork for the rest of the class and understanding what you're doing. So let's get started. So first of all, remember the role of dimensioning is to define the size and location of the features of the part. Features being holes, cylinders, things like that. It could also be to define the size of the part, the overall length, width, thickness, the location of different features, location of surfaces, locations of holes and cylinders, all those things. So dimensions define the size and location of features. And features is an important term. You'll hear this over and over again in this class. So just be ready to understand and to really grasp hold of the concept of features, especially features of size. Dimension application requirements are governed by the latest dimensioning and tolerancing standard, which is the ASME Y14.5-2009 standard. And this is one of the statements from the standard. Proper application of size and location dimensions, in addition to tolerances, provide complete dimensional control of the part. So that's what we're trying to do. We're trying to define the complete dimensional control of the part, okay, through application of dimensions. So when we talk about location and size dimensions, or size and location dimensions, it helps to understand or to see the part as being composed of different three-dimensional geometric primitives, okay? And we can define these primitives so these are the three-dimensional geometric primitives, as a prism or box shape, as a cylinder, as a pyramid, as a cone, as a torus, or as a wedge. Okay, so those are the 6 geometric primitives. I left out torus on that. A torus is basically a donut shape, so that needs to be thrown in there, but that's kind of on the perimeter, so to speak, because we don't often see it. All right. So those are the geometric primitives. Each one of those primitives has a positive and negative side of it, right? So a positive cylinder, like we see here, is a cylinder that you can touch, right? A negative cylinder would be a hole, right? And you can't touch a hole. It is just the lack of material. But that would be the corresponding negative cylinder. All right. So each one of these shapes, each one of these three-dimensional primitives has a positive and a negative side of it. So in this example here, we have a part that we are kind of deconstructing into its three-dimensional primitives, and you can see we have a positive prism here. That's a box, right? We have another positive prism. All right, so it's composed of these 2 positive prisms or boxes put together. We also have a series of 4 negative cylinders. We have another negative cylinder here. We have a positive cylinder here, a smaller negative cylinder in the side, a negative cylinder going down through the positive cylinder, and then finally a negative cone. All right. Now, when we put all those things together, we get this corresponding three-dimensional complex shape. if we were dealing with CAD, we might call this a composite solid because it's made up of a bunch of three-dimensional primitives, 3D primitives. Now, this is going to help us to not only understand the part, but to understand how to dimension the part, right? Because when we assign size and location dimensions, we want to dimension the sizes of these individual three-dimensional shapes, right? And then we want to locate these three-dimensional shapes. And so that helps us to break things down into bite-sized chunks, essentially. All right. Now, this should be something that you've heard before in the 101 class, maybe in other classes as well, but it's something that is going to be very important to carry through this class. All right. So when we talk about dimensioning, the application of dimensioning, there's certain terminology that we need to be familiar with. The dimension line is the line in between the two arrows here. Okay, so that's called the dimension line. The extension line is the line that extends from the edge of the object out, and the dimension line rests in between those two extension lines. And then when we point to an object, such as a hole or cylinder, and we assign a dimension to it, that's called a leader. That line right there, this line right here is called a leader. So dimensions are composed of dimension lines, extension lines, and leaders. With extension lines, we want to have a gap in between the edge of the object and the beginning of the extension line. We do not want to have a gap here where the dimension line crosses an an object line. Okay, so that we want to avoid that. Now, the good news is AutoCAD does that automatically, or most CAD packages. In fact, probably all CAD packages do that automatically. But since we're not using CAD, you have to be aware of kind of the rules for dimensioning that we take for granted when we're using a CAD system. Okay, so this is the correct layout for dimension and extension lines. Extension lines may not cross dimension lines. So this is okay. Why is this okay? Well, because this is an extension line crossing an extension line. That's fine. This is not okay. This is not okay. Why? Because this is an extension line crossing a dimension line. All right. So we don't want this. We want this. There are 4 ways to apply dimension lines. We can apply them arrows on the inside and dimension values also on the inside. We can apply them arrows on the outside, values or dimension values on the inside. Arrows on the inside, values on the outside, or arrows on the outside and values on the outside. Okay? 2 dimensions may share an arrow, and smaller dimensions should be placed closer to the object. So let's see in this example, how these are applied. So in this first one at the top, this 5.6 dimension, the arrows are on the outside and the numbers are on the outside. So you can see the arrows on the outside of the extension line and the number. Now in this example, the 101.6, the arrows are on the inside of the extension line and the number is on the inside between the extension lines. Moving down to the left-hand side, this 12.7. In this case, we see the arrows on the outside of the extension lines, but the number in this case is on the inside of the extension lines. And finally, this example, we have the arrows on the inside and the number on the outside. Now, again, we take this for granted because AutoCAD and other CAD systems, Inventor, Fusion, whatever, do these for you. All right. But it is important that you understand what these CAD systems are doing. And in the case that sometimes the CAD system doesn't do it right, you have to correct it. Or in the case that you're doing it by hand, as in this class, you need to be able to apply it properly. Okay. Here's some examples of dimension text. In this case, these are local notes, right? A general note applies to the whole drawing. A local note is typically applied with a leader pointing to the object in question. In this case, the stock thickness or the blend. These are leaders connecting the local note to the object. This down here is a general note because it applies to the whole drawing. Notice it doesn't have a liter, right? So this says hot rolled steel is 3.797 plus or minus 0.025 thick. That for the material that this object is made out of. All right, dimension systems, right? We use the system on the left-hand side universally, right? Metric or inches, it doesn't matter. In the United States, ASME Y14.5 standard, we use the unidirectional system. Overseas, in Europe, they use what's called the align system. This is where, notice, you can see it most clearly on the side dimensions here. So the 3810, the 3759 tolerance dimension here is unidirectional. That is, we can read it from a horizontal orientation. But over here, this dimension over here, notice that it's turned sideways. So this is the European system, all right, the align system. It's also used in architectural drawings. ISO is the International Standards Organization for the equivalent of ASME in Europe. Okay, so liters. How do we apply liters? Well, we generally want to apply liters at an angle in the white area here. Okay, so we want to avoid liters in the angle in the red area here. So you can see this example right here. This is not good, right? That angle that the liter is at lies in this red zone here, and so we don't want that. This is better. This is better, all right? It's kind of roughly at a 45-degree angle. Notice that these are okay. When a liter, we really can't avoid a liter crossing object lines and dimension lines, or excuse me, extension lines, all right? And in fact, crossing dimension lines. All right, so this is fine. The measurement system in the U.S. with the ASME standard, there's two customary systems. We have the inch system and the metric system. The U.S. customary inch system and the SI or metric system. Okay, most countries outside the U.S. use the metric system, as we all know. There's no difference in application between dimensions in either measurement system. Now, there is a difference in how decimal places are specified in the metric and inch system, and that helps us to understand what we're looking at, okay? But there's no difference in the application between inch and metric in the ASME system. So here's some examples of the decimal inch system. By the way, all dimensions shall be applied in decimal format. That is one of the rules of the ASME Y14.5 standard. So we only use decimals, no fractions. All right. So in the decimal inch system, we want no leading zeros, right? So we want 0.500 as we see up here, not 0.5. Okay, no leading zeros. We also want trailing zeros to be shown. All right, so 0.500. These two zeros are called trailing zeros. We want to show that in the decimal inch system. We typically use 2 or 3 decimal places in our inch drawings. All right, typically 2 or 3. We can use more depending on the level of accuracy that's required. Okay. Or excuse me, the number of decimal places that are required, right? So if we have a 5 way out here, then yeah, we gotta have 4 or 5 or 6 decimal places, all right? The number of decimal places, however, does not affect accuracy, right? So these are all treated as the same. Round off decimal values converted from fractional dimensions. So when we're converting from fractions to decimals, we want to round off the decimal values. We're not doing that in this class, so we don't really have to worry about that. Now, switching gears to the inch system, the metric system. In fact, we're doing the opposite. Show leading zeros in the metric system. So 0.5, yes, not 0.5. All right, you can see it in this example right here. All right, zeros, 0. We do not show trailing zeros. So again, the opposite of what we do in the decimal inch system. So 0.5 is correct. not 0.500. So these two trailing zeros would not be shown. 10 instead of 10.00. Again, no trailing zeros. Right? There's a couple of rule breakers with the metric system. So when we have limit dimensions like this example right here, the 37.70 and a 31.67, when we have limit dimensions, we want to balance the number of decimal places. So because we have 2 decimal places here, we need to have 2 decimal places here, which means in this case, we're breaking the rule for not showing trailing zeros, and we're including the trailing zero here. The other rule breaker for the metric system is, and it's kind of a weird one, for unidirectional dimensions, right? We are not going to show the sign, and we don't show any trailing zeros. So this right here would be what we would show for the 47.7 plus 0 minus 0.05. All right. This was a problem in AutoCAD for a number of years. AutoCAD refused to do this. The latest versions of AutoCAD, a couple of years ago, they updated it, allows this kind of proper formatting. All right. Now, continuing with dimensioning systems, there's a couple of strategies that we can employ when we're dimensioning. All right. There's 3, in fact. So these systems are called the chain dimensioning system, also known as continuous or point-to-point, the baseline dimensioning system, also known as the datum dimensioning system, and the coordinate dimensioning system. Okay, we're not really going to talk about the coordinate dimensioning system. That's most commonly seen in CNC applications or machining applications. But we will look at chain and baseline dimensioning. Basically, which system you use should be based on the part function. All right, dimensions should be applied according to part function. An example of a datum or baseline dimensioning system is shown here. In this case, we establish some datum surface right here, and then all the dimensions start from that. So a datum surface or baseline surface, and then all the dimensions go from that. In the chain or continuous dimensioning system, we again establish a baseline surface, but then we chain the series of dimensions from one to the other. So these holes are dimensions based on their previous hole, the other holes, so to speak. There is a problem with the chain dimensioning system, and that is that it allows tolerance accumulation. All right. We don't see this in the intro to drafting class because we don't do anything with tolerances, but we do experience and see this with the detailing class. So if you've had the MDT 110 class or the detailing class, you will know what we're talking about here. This is a very important concept, and why we don't use chain dimensioning, in general, why it's to be avoided. So in this case, notice each one of these dimensions has a plus or minus 0.02. So if in this chain dimensioning system, if this surface actually is manufactured at a location of 1.27, that's acceptable, right? We establish this as our baseline, right? This is our datum surface. So if we put 0.02 tolerance on this red line is the acceptable surface location here. But notice what it does to this dimension. So now this dimension is, again, within the tolerance range, 0.02, so 2.02. But it's already starting 0.02 from here. So now this surface, this red line indicates where this surface would be, is again pushed 0.04 inches to the right. So we have a tolerance of 0.02 acceptable, pushing this surface to the right. The tolerance accumulation means we have 0.02 again, and then 0.02 further, and you can see it just carries on. So this surface would be out here, And then the ultimate, the total response here would be this surface gets pushed way out here. And now this is what happens when we have tolerance accumulation. The accumulation of 0.02 inches all the way to the right affects this surface, pushing it all the way out 0.08 inches past where you intended it to be. And oftentimes this is unacceptable. All right. And oftentimes this is not something that is readily seen. And so that's why we need to avoid this chain dimensioning system as much as possible. Same thing can occur with a baseline dimensioning system. When we establish the baseline, this 0.02 will push this surface to the left or to the right. So in this case, notice we're taking 0.02 away. So it's 4.23. This surface right here is moving to the left 0.02, which is acceptable, right? It's within the tolerance range. But notice how it negatively affects this surface. All right, so those are things that we have to be aware of. So what's the proper way to dimension? Well, we should use what's called direct dimensioning. That is, we apply dimensions based on part function. All right. This means that we need to know mating features and functional requirements, which is the big problem here. Oftentimes we do not know, in class, I should say, in our classes, we don't know what the mating features are, and we don't know what the functional requirements are. All right. And that is because oftentimes we're given just parts. Hey, here's a part, dimension it. In the real world, we know what the mating features are going to be, and we know what the functional requirements of the part are going to be. All right. So this is a problem that we have in education, in learning about this, where we have to kind of play this game of make-believe, where we have to make up some mating features and functional requirements. So mating part dimensions, i.e. functional requirements and mating conditions. So in this case, we have a block, a square block that's going to go into this hole, this square slot. So we dimension the total width of the square block, and then we have a mating dimension which corresponds to that. Think of this as a pin and a hole. We have the diameter of the pin, in this case the length of the part or the width of the part, and then we have the diameter of the hole, in this case the width of the opening. And so these are called mating dimensions right there. Another mating dimension, the location of these holes that are intended to align with these holes. Notice we dimension it from this surface to the center. So we want to go to the mating surface to the center. All right. So all these are mating dimensions, and mating dimensions are good. We should use them as much as possible. They will make, and especially with geometric dimensioning and tolerancing, it not only is something that we should do, it is something that is forced on us. All right. It is mandatory in order to apply geometric dimensioning and tolerancing properly. All right, so let's kind of look at our dimensioning rules and guidelines. Some of these we've already talked about. Most of these should be a review from your previous classes. Dimensions based on mating conditions and functional requirements. Dimension where the feature contour is shown. Dimension between views, right? Top view, front view, dimension between views. This does not mean connect dimensions between views. It just means place dimensions between views. Dimension outside of the object. Do not put dimensions on the inside of the object. Do not dimension to hidden features. That's a big no-no. Do not repeat dimensions between views or within the same view. Do not provide superfluous dimensions. That is dimensions, also known as double dimensioning. Dimension features where they're shown in true shape and size, especially relevant for auxiliary views. Do not connect views with extension lines. I already talked about that. Notes are an important part of dimensions. And finally, use standard abbreviations where symbols are not applied. All right, so an example of double dimensioning or superfluous dimensions. So this is an example of double dimensioning. We have one too many dimensions here. We need to get rid of one of these dimensions. Either the 0.75s, one of the 0.75s, or the 225. One of these has to go. Which way should we go? Well, that's based on the functional requirements and mating conditions. Okay. All right, last thing we're going to look at, I'll do an example of this calculation. But again, if you've had the detailing class, the 110 class, this is going to be a review. As I said, I will do a review of this calculation. But we have three mating part conditions. We have clearance fits, interference fits, and transition fits. A clearance fit is when the hole is larger than the shaft, right? So we have clearance. An interference fit is where the hole is smaller than the shaft, right? So we can't just put the shaft inside this hole. We have to force it in. And finally, a transition fit is a little bit of both. Basically, a transition fit can be thought of as a snug fit. You're going to get the hole into you're going to get the shaft into the hole. But you may need a little bit of force, or you may need to wiggle it a little bit. That's called a transition fit, where you have a little bit of clearance and a little bit of interference, depending on the range of sizes, right? So these mating part fits rely on tolerances. They rely on tolerances. Important equations, and I will go through this again in a demo. The allowance is the minimum hole minus the maximum shaft. When we have a positive allowance, that's called clearance. A negative allowance results in interference. When we have an allowance of 0, that's called a line fit. Minimum clearance is equal to the minimum hole minus the maximum shaft, and maximum interference is equal to the maximum shaft minus the minimum hole. Negative features include holes or slots, and positive features include cylinders and tabs. And finally, the mating part fit equations, the maximum material condition, again, a huge term, a huge concept in this class, maximum material condition, exists when the condition of a feature with the maximum amount of material is within the dimensional tolerance. Okay, let me read that again. The maximum material condition, MMC, is the condition of a feature where the maximum amount of material exists within its dimensional tolerance. So for a hole, the MMC size of a hole is the minimum diameter. Why? Well, because that results in the most material surrounding the hole. For a pin or shaft, the MMC size is its maximum diameter, because obviously that's the largest amount of volume for that pin or shaft. Now, when we go back and we look at these three equations again, but in terms of MMC size, the equations get a little bit simpler. The allowance is the MMC size of the hole minus the MMC size of the shaft. The minimum clearance is the MMC size of the hole minus the MMC size of the shaft. The same equation, right? Same equation, just different term, different name. But the maximum interference, we just flip these two around. MMC shaft minus MMC of the hole. So really, the fundamental concept here is that we want to pay attention to the MMC sizes of the positive and negative mating features. The hole is the negative feature, the shaft is the positive feature, the MMC size. All right. So that takes care of this presentation for Chapter 3. Hopefully this was a good review for you. If it wasn't a review, if this is all new concepts, then you really need to dig into that chapter, Chapter 3, because a lot of these concepts we're going to carry on through the rest of the class. All right. I will do a demo or an example problem of these mating part fit equations, and I'll upload that to Canvas as well. All right. See you in the next video.